Welcome to another data science deep dive on our technical track. In the following presentation, Kenny Wenqing Chen, data scientist at TikTok, talks about how it's critical for advertisers to spend resources efficiently and effectively on the right groups of audiences. He dives into introducing cutting-edge machine learning methodologies that help advertisers determine, given user traits, the audience segments which yields the highest ad effectiveness. Enjoy.
Hi, everyone. First, I want to thank you for taking some time out of your daily schedule to participate in this presentation. So basically, in today's talk, we're going to focus on how to use machine learning methods on historical data to determine what the best subgroups are for advertisers to target in the future. So before we dive into our topic for today, I'd like to briefly introduce myself and sort of just go over what to expect and what not to expect from this presentation. As you know, I'm a data scientist currently working at TikTok, and previously I was trained as a social scientist academically with a focus on answering political questions, right? And the nice thing about social science field and ad industry is that there's a lot of similarities between these two fields, right? So one of the fundamental problems that both fields are trying to solve is the question of what would have the outcome changed had some covariates changed, right? For instance, if you study political science, if you're particularly interested in election, and one of the bigger questions is, for instance, what would have the election outcome been had a candidate not been an incumbent, right? So this sort of incumbent effect sort of drives the election with the assumption that, incumbent candidates, they hold more resources, so maybe they're more likely to win. So there's research going to compare the users, which is the candidates, with or without incumbency. And they're trying to find out that treatment effects between the treatment and control groups, right? And also, so in the ad industry, with respect to advertising effectiveness, we ask pretty similar questions, right? If you think about the question I just asked and replace the outcome variable and covariate with what we are interested in right now in advertisement industry, you can have the same very similar questions asked, right? For instance, you can ask, what would have the outcome changed? And the outcome being maybe sales, maybe brand metrics, or maybe every other interested response variable that you're interested in learning had a person or a household been exposed to someone's advertising campaign, right? By laying out these two very similar questions, we know that these questions that are asked by both fields, they're actually causal in nature, right? So this similarities that explains what I'm here and this what I'm passionate about. Actually, I love answering this type of causal questions, and I love using the solutions to help people. And right now in ad industry, I love helping advertisers to make informed decisions based on data available. So before we dig into the topic today, I want to give you a bit of a roadmap about what this presentation is about and what are the assumptions I'm making in terms of the knowledge of the audience and also what this presentation isn't about. Right, so first, this presentation is about understanding the importance of audience targeting. And it's about showing you some of the common mechanisms of audience targeting and why some of the current practice in the industry of finding the best audience segment to target is maybe not the most optimal solution. And later, I'm going to introduce some of the most recent work in the machine learning world that could potentially help you find those treatment effects at a more granular level. Hence, it's going to help us define what the more useful subgroups are for advertiser target in the future. So this talk is an intertwined between machine learning methods and causal inference. So I assume, because of time constraint, I'm assuming that the audience has some sort of a basic knowledge of causal inference, because we probably won't have time to go through step-by-step what causal inference is and what are the contributions of the field is. And now let's talk about what this presentation isn't about, right? So this presentation is not about showing you any approach adopted by any product, by any company, right? And this presentation is also not about a detailed tutorial about how to implement a certain kind of machine learning methods. So we're not going to be able to show you from end to end how to ingest the data, how to model the data, and how the outcomes will look like, right? This is not a hand-holding tutorial session. And finally, this does not take into account this very recent iOS update and the implication of such update on these machine learning methods. But however, I do recognize that these improved privacy regulation is very important. And I do believe that everyone in this ad industry should work together and try to understand what the implications are. So I'm open to any kind of exchange after this presentation. So now let's talk about what is audience targeting, right? So there are many mechanisms in practice right now in today's advertisement industry that we could actually target audience. So I'm just showing you like the most common mechanisms that's available right now for advertisers when setting up a campaign. So many more, but I'm just showing you the most important three that I believe so. So namely, there's contextual targeting, there's remarketing, there's behavioral targeting. And these mechanisms vary in the level of user information used while selecting the ad. Right? So when you're thinking about contextual targeting, it actually involves matching the ad with the context of the website or web page that is displayed on. And we're doing contextual targeting, which basically ignores the visitor's interest profile. Right? For example, if you want to think about, let's use a car insurance company as example. So if you're a car insurance company, you're gonna want to place advertisements on car-related websites or web pages, right? Because it assumes that the visitors to this website are likely to either own a car or want to own a car, right? Hence, we're assuming that these group of users will need car insurance. So we know that with contextual targeting, we actually expect visitors of these websites with different interest profiles will probably see broadly the same kinds of ads. And these will match the topic or the context of the particular website or the related category. Right? And then it's remarketing, right? So remarketing is a very specific mechanism used by advertisers to target users who have indicated very specific interest in a particular product, right? So for instance, if a user go to a product website and shop the particular product, it sort of indicates that there's a very specific interest in this such product, right? So let's come back to our car insurance example, right? So say a user went to a car insurance website, clicks on the link to get a quote, but leaves without finalizing the purchase, right? And then this insurance company can then place this remarketing ads into other websites that the user visits, right? Which is usually unrelated to any car insurance or cars or insurance, right? But this car insurance company actually placed the ads and trying to tell this users like, hey, we're giving you probably 20% discount, and would you come back and finish that purchase, right? So the purpose of this kind of remarketing targeting is to sort of lure the user back into finish that purchase. So here the advertiser exploits a very narrow and explicit signal from the user to target their ads. And then we're in behavior targeting, right? So behavior targeting is actually used to select a very few related ads from a large category that is shown to the user. And this filtering is done based on the user's interest profile, right? So this particular mechanism goes beyond the single domain that we just talked about when we're talking about remarketing, right? And instead, this mechanism selects ads that might relate to the user's long-term online interest. So with behavioral targeting, the users might see the car insurance related ads on the website or web page about food or nutrition simply because the user visited multiple different car insurance related websites. So this type of targeting sometimes could be controversial because it relies on the detailed analysis of user online behavior. It tracks people's online behavior, and it sometimes results with ads that might be somewhat dissonant with the page that's being viewed. Right, so this is what audience targeting mechanisms are in general practice in the industry. So now I'm going to talk about, we talked a lot about users' interest profiles, right? So we need to understand users' interest profile so that we could, if we want to retarget the audience, we need to know what essentially are users interested in, right? So what I want to suggest here is to understand users' interest profile, we could use the result of advertisement effectiveness, right? So one way of understanding that users' interest profile is to look at advertisement effectiveness and see if an ad or a campaign can effectively change the user behavior, right? So the assumption is that if an advertisement can change people's behavior, that could prove that the user actually is interested in the either content or the goal of the advertisement, right? So some of you might have worked in advertisement effectiveness as a subfield in this industry for a while. So we all know that most ad effectiveness products or research involves either randomized control trials, randomized experience, or sometimes we call it A/B tests, or treatment effect estimation with various methodologies when we work on historical data, right? So both of these randomized controlled trials and also treatment effect estimation using historical data, what we're trying to get is we're trying to try to get at two things, right? One is the average treatment effect, which is essentially if you suppose you run an A/B test, you're trying to understand the difference between the outcome between the treatment groups and the control groups, right? And that's usually called the average treatment effect, which is just the effect of the advertisement. And we could also want to obtain the average treatment effect of the treated, which essentially it's very similar to average treatment effect at some points, but essentially it's just the effect of the ads on the users who are actually exposed to the advertisements. And that's just overall metrics we want to obtain after running either an A/B test or observation study to estimate the causal effect, right? And sometimes when you finish this analysis, advertisers might come back and ask, okay, now we know that overall, we know that there's an effect of my campaign, say if it's positive and significant. And for instance, if there's a gaming ads advertisers, right? So if they want to know that, okay, now you have proven that my ads is effective, overall, positive and significant, but now what do I want to increase the ROI, or if I want to make my ads more efficient, exactly what are the groups that I need to focus on next time if I want to do similar things, right? And this is sometimes in practice, we usually suggest advertisers, okay, now we're making some assumptions. If you are a gaming ads company, that we assume based on past experience, maybe your gaming ads would work better on younger generation as opposed to elderly generations, right? So we sort of assume that, okay, now we could help you look into a pre-specified subgroup and run analysis on that group, right? And by now you probably know that, okay, now you're making an assumption. For gaming, it's easy, right? So based on past experience, maybe younger generations, or there's a particular group that we already know that's probably react better than the others. But sometimes advertisement, you don't know, right? And we're trying to make data speaks to itself. But what I just described does not let data speak to itself, right? We actually pre-specify the subgroup and run analysis, right? So you can see that subgroup analysis with pre-specified groups, there are kind of issues, right? Even if you run the randomized controlled trials, and even if you plan very well ahead of time, and sometimes you just need a huge power for this type of very granular subgroup analysis to work, right? Because most people, right, so just like the example that I just shared with you, sometimes people can just cherry pick and whichever subgroup that's convenient for them, right? So we're not actually letting the data talk, right? So what I'm going to propose here today is just a review of very recent literature in machine learning. They actually indicate that we could use the data, right, without making any assumption of the subgroups. We just let the data talk, and we can learn from the data, and we can learn about the importance of these kind of subgroup analysis. And we can learn about what drives the treatment effect heterogeneity. So these new machine learning approaches can inform us to answer this kind of questions, such as, who should we treat? Or using our advertisement effectiveness jargon, it's like, who should we make eligible to send our impressions to? So here I'm just going to bring up like some of the more recent machine learning literature that can actually help us achieve that goal. And as I was alluding to like earlier in the beginning of the presentation, like recently we're actually seeing that there is a big way of machine learning researchers working together with social scientists and statisticians or econometricians, right? So they're trying to bring together the best of the two worlds, right? We all know that what machine learning can do so far, right? So machine learning, simply put, it could just efficiently detect patterns in high dimension space, finding relationship between variables with greater degree of accuracy. So in plain English, machine learning is a very good tool to predict better than traditional statistical or econometric techniques, right? But however, as I described earlier, this type of advertisement effectiveness question they're usually causal. Right, so traditional machine learning algorithms, they're not equipped to answer this kind of question. So I think there's a very interesting push in recent years that they're trying to combine machine learning and try to use machine learning algorithms to solve for causal inference problems. So again, because of the time constraint, I'm not going to be able to finish introducing every single piece of work that I'm just listed here. So if you're interested, I'm happy to talk about it after the talk. But these are the things I find quite relevant here, right? So I'm going to just be focusing on one of them, but just to give you the overall, very high level summary of what these three strands of research is about. If you look at the first bullet point, so the first strand of research, they're pretty ambitious, right? So what they're trying to achieve is just to estimate the conditional average treatment effect function, right? So essentially what they're trying to do is they're trying to map someone's observed covariates, such as age, gender, education, income, DMA, and so on, into the outcomes, right? To simply put, what this gives us is, if we know someone's observed covariates, we're going to be able to predict what his or her treatment effect is going to look like, right? So you can see that Athlete Bishari Vogler back in 2019, and they're at Stanford, and Kuznets Khan, they're at Berkeley. So these are the things they're trying to get at. And the second strand of the research cares about what is the best treatment assignment rules that could give us a maximum expected gain, right? So this is relatively new, so they just published the paper this year, but they don't care about what predicts the outcome, and they don't care about what is the exact amount of the prediction is, but instead they care about how should we assign the treatment assignment, right? And these first two approaches have very strong foundations in semi-parametric theory and statistics, right? So you can see that. So there's a sort of combination of convergence between that semi-parametric statistical theory, and they use a lot of machine learning here. So the final strand of research I want to talk about, briefly touch upon, is less ambitious, right? They're not trying to directly tell you what predicts what, right? Instead, they're not going to estimate directly the conditional average treatment effect function, but instead look for subgroups of units who would have the highest and lowest treatment effects, right? So we won't be able to know exactly how much that response is going to be predicted to be, but we would be able to know what predicts that outcome, right? So that's just a very high-level overall summary of what these strands of research is. But again, given the constraint, I'm only able to talk or summarize what Effie and her colleagues' work is about. So I promise you in this presentation, this will be the only mathy slides that you'll see. So please bear with me. So I will go over this at a very high level, but if we have any questions, we can talk about it in our Q&A sessions or after this presentation, right? If you look at the first equation, I'm trying to simplify it. So basically, it's very simple, right? So y is the outcome variable that depends on a set of covariates in a non-parametric way with some additive treatment effect tau and some error term, right? And here you see the tau of x, right? So that means your treatment is actually dependent upon some covariates. If you remove that x, you're actually saying that your tau is homogeneous. And now that we're adding the x, that means your treatment effect is actually heterogeneous, right? So imagine the world that the tau does not depend on the covariates when it's homogeneous. And how do we estimate that tau, right? One trick we can use to find a good estimator of the treatment effect, we can simply do it by residualizing both the outcome and the treatment variables, right? So essentially, we're just using the predictive version and subtracting them by their own values, right? For instance, how do we residualize the treatment assignment variables, right? So by residualization, we mean that you can just take that treatment indicator and minus its propensity score, right? And to residualize the outcome variable, essentially, we just take the outcome variable and minus its conditional expectations, right? So these are usually called the pseudo outcomes. And the propensity score and the conditional expectation that I just mentioned, we could actually obtain them through machine learning, and sometimes called during the double machine learning, right? So that's that. But if we come back and look at the tau, which is dependent on a set of covariates, that is the heterogeneous treatment effects. And how we do that, it's the same, right? So if we want to extend that partial linear model to allow tau to be able to depend on the set of covariates, we can still use a simple regression solution, but we can just estimate that tau in the small neighborhoods. That's why you see in the second bullet point, you see this n of x, n means neighborhood. So we can do it in this small neighborhood, and we're actually hoping that these treatment effects will be pretty similar because their x is similar, right? And those treatment effects in this small neighborhood, we just call it local treatment effect, And if we do it in many neighborhoods that have similar covariates. And now you probably have questions, right? Because I'm talking about doing very simple regressions in the small neighborhoods. It's like, how do we pick that neighborhood, right? So I think that's where the contribution of Effie and her colleagues are, because they have contributed to the literature. They have suggested we could actually use machine learning algorithm to help us determine what the neighborhoods are, right? And the nice thing about the research is actually they use the off-the-shelf, like random forest algorithm that everyone knows about, and it's off-the-shelf, and they just make some changes to its loss functions, and they actually modify the splitting criteria so that they can help us estimate a sort of conditional average treatment effect. Right, so that's the mathy part of this presentation. So I'm just going to use plain English and sort of summarize what that mathy part gives us, right? So actually, if you look at the plot, this plot is I directly took it from Effie's paper. So what they built, so what they modify is random forest, and they call it causal forest. So they're going to use causal forest to estimate the treatment effect heterogeneity, right? So basically what their causal trees and causal forests do is to generalize the splitting rows of the traditional random forest, right? So the traditional random forest are trying to minimize prediction errors, but now they don't want to do it because it doesn't really give us any causal estimation, right? So instead, their version of random forest is to maximize the treatment effect heterogeneity, right? So instead of obtaining that prediction on the partition of data, so causal forest actually estimate the treatment effect on the partition of data. And remember in the previous slide that we wanted to go over the small neighborhoods to estimate the treatment effect. This is exactly what they're doing, right? This pod doing. So basically they're, sorry. Okay, so we want each leaf here in this model. So you can see that at the end of each branch of this tree, the purple block is one node. Right? So what they're trying to do is, for each branch, at the end, you should have treatment and control groups that have very similar covariates. But however, between leaves, those covariates should be different. And if you repeat it again and again, which is similar to traditional random forest, if you start growing all these causal trees and form a causal forest, and you're able to get a good estimator. And in their paper, they actually have a very nice proof that actually have proven that there's really nice property about this their method, such as asymptotic normality, and we can actually make inference from it just because it's based on the resampling from the forest. Okay, so lastly, I want to sort of showcase that how we could use causal forest in the real world, right? So I'm going to use the data as a toy example. So it does not come from any company. So it's just a toy example, right? So suppose like there's company X, and we can use a gaming company as an example, right? So there's a company that wants to run a gaming ads or gaming ad campaigns to improve its lower funnel objectives, say install or sales or purchase, right? For instance. And after, okay, now after running those campaigns, they collect the data, you do analysis, and you say, okay, now we have positive lift, or we have positive significant average treatment effect. And the advertiser sometimes will come back and say, okay, now on average, you can tell me that my campaign is effective. But how do I, if I want my campaign to be more efficient, if I want to increase my ROI, I need to focus on a specific subgroup in the future, right? So this is where causal forest came in handy, or any type of machine learning methods that can actually estimate this causal conditional average treatment effect comes in handy, right? So we could replicate what I just shared with you, and then we can, for instance, in this case, you can see that, okay, now, even though on average the effect is positive, but if you break it down in the more granular level, you see that actually that the campaign, the advertisement campaign, is more effective in Italy, Germany, and France. Right? The effect is positive in U.S., Canada, Great Britain, and Spain, but we don't know for sure because given that effect error bars spans from negative to positive. Right? But we're pretty sure that in Italy, Germany, and France, you're going to see a positive and insignificant effect. And you can do that on continuous variable as well, such as age group. So you're able to tell, like, under what, between what age ranges that you're going to have the most effective advertisement campaign, right? And this implication for the advertisers is like, in the future, if you want to increase your ROI, or if you want to know, like, exactly what subgroups I should target, we're actually letting the data talk. We're not making an assumption of what subgroups that we should focus in the first place, right? We're actually using machine learning and letting data decide for itself. So this brings me to the end of the presentation. So I want to give you a little summary, and I'd love to hear from you. So in this presentation, first, we sort of introduce and walk you through some of the common mechanisms to target audience. And then I suggest, and my argument is that we could use the ad effectiveness results to proxy user interest profiles. And I introduce you one of the more rigorous methods to identify treatment effect heterogeneity, as opposed to make assumption and use pre-specified subgroup for analysis. So this brings me to the end of the presentation. So I'm open to discussion, and if you have any questions, please let me know in the Q&A sessions, and I'm open to any type of exchange. Thank you.
This was Kenny Wing Chen Chen, data scientist at TikTok, with his presentation on introducing machine learning methodologies that help advertisers determine the audience segments which yield the highest ad effectiveness. If you'd love to watch more content like this, you could subscribe to Data Science Insider, a program where you could see a complete on-demand video library and watch it whenever you want. The link is in the comments.